but it gives us a place to start if we wanted to start to find all of the factors. All right, so let's use this. We're gonna have to find the zeros, find the rational zeros of this polynomial. It's a cubic, so if we found just one zero or one factor, then we'd be down to a quadratic, and that we can solve, right? All right, so let's do this on my paper. So let's move over here. There we are. Let's see, so you can see it. Use the rational zero theorem to find all the zeros of this function. Okay, so this is going to be pretty good because one of them, so the factors of 1 are just plus or minus 1, right? The factors of the constant term. Factors of 2, right, the leading coefficient, are just going to be plus or minus 1 and plus or minus 2. Sorry, I wrote that kind of funky. All right, so the possible zeros are going to be plus or minus 1 and plus or minus 1/2, right? This over this or this over that. So we've only got 4. So let's try them. Now we've just got to try. I'm going to try the ones first because those look easier. Let's try using synthetic division. The coefficients are 2, 1, -4, and 1. So I bring that down, add, multiply, add, multiply. Ta-da! Let me see if I can focus this better. There we go. That's better. Yes, we got a remainder of 0. So what does that mean? That means that x minus 1 is a factor of that function. And we can write the remainder is going to be 2x squared plus 3x minus 1. So we've got a quadratic. We can solve it. Is this going to be easy to factor? Not sure. Let's use the quadratic formula. So x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So minus 3 plus or minus, let's see, 9 plus 8, so square root of 17 all over 4. Okay, yeah, it does not look like I was going to be able to factor that. Oops, bring that over. Did we do that right? 9 plus 8, yeah. Okay, so these are the other two zeros. So what did they ask us to find? Find the rational zeros. So yep, the rational zeros are x equals 1 and -3 plus or minus the square root of 17 all over 4. Let's make sure that's the same thing they got. Oh no, did I do something wrong? I must have done something wrong. Minus b plus or minus the square root b squared minus 4ac all over 2a. 9 plus 8 is 17. Okay. I don't know. Oh. All right. What we did was, we did this right. Sorry. Sometimes it's okay to get a little confused. Sometimes your teacher gets a little confused too. So they were asking for rational zeros. 1 is the only rational zero. We found all the zeros. Are these rational? They're not. Square root of 17 is not a rational number. Okay, so we just went a little bit extra. Okay, so these are all the zeros. This isn't rational. But we just went ahead and found it anyway because we're just like that, overachievers. But this is the only rational zero. Okay, so anyway, don't worry about me. All right, so let's go back No, this wasn't working last time either. Okay, here we go. We did it. We found the rational zeros of that polynomial. Okay, so let's talk about the fundamental theorem of algebra. Okay, this says we have a polynomial of degree n. Then it has at least one complex zero. Does it have to be imaginary? No, like 2, a 0, 2 would be a complex zero, right? So it's just saying if you have a polynomial, it's got a 0. And it could be complex, but we've got a 0. So what this is saying is you can break down any polynomial. So once you know one that's true, then you can find the next 0 and the next 0. And this is saying if you have a polynomial of degree n, it has n roots. Okay, that's all this is saying. If you have a 5th degree polynomial, it has 5 roots. If you have a 12th degree polynomial, it's got 12 roots. Some of them might be complex. Some of them they says if we allow for multiplicities, right? So we might have an x minus 1 times x minus 1 times x minus 1. A bunch of the roots might be the same, might have multiplicity greater than 1, okay? But if you've got an nth degree polynomial, you have n roots. Okay, so that's kind of like what we just did in that example. We had a 3rd degree polynomial. We found all 3 roots, even though that wasn't what the question asked us to do. So if we have a 3rd degree polynomial, we can find 3 roots. All right, so the things that we just talked about are going to be tools that we can use to find those roots. So first, we can use the rational zero theorem to list all possible rational zeros. We just did that in the last example. Then we can use synthetic division to try them out, right? Keep going until you have a quadratic. Okay, once you have a quadratic, you win. You can solve it, just like we did finding the non-rational zeros of the last problem. Once we have a quadratic, we can either factor or use the quadratic formula to find the remaining 2 roots. And then find the zeros for the quadratic function, either factoring or using the quadratic formula. Okay, so basically that's just what we did in that last problem. List all the possible rational zeros, use synthetic division to test them out, and keep going until you get to a quadratic. All right, so let's try this one. Example 5. Find the zeros of this polynomial, 4x cubed minus 3x minus 1. All right, so just like last time, it's asking us, but this time it's actually asking us to find all the zeros, whether they're rational, whether they're complex, whatever, okay? All right, so the possible rational ones, factors of -1 are going to be plus or minus 1, and factors of 4. It could be plus or minus 1, plus or minus 2, plus or minus 4, right? All those factors are the leading coefficient. So possible rational roots. Could be plus or minus 1, right? This over that. Could be plus or minus 2, this over that. Could be plus or minus 4. So you have 6 possibilities. And now we just got to test them out. Okay, this is a cubic, so if we find just one rational root, then we've got a quadratic and we're good, right? So we've got to just test these out, and hopefully one of them works for us. So we'll use synthetic division. So the coefficients are 4, 0, -3, -1, right? Don't forget the 0 because we're missing an x squared term. Got to have that there. So we bring that down. Add, multiply. Once again, our first try worked. That is just luck. Okay, sometimes you're going to have to try 2, 3, 4. I honestly didn't know the answer, and it was just lucky both times. I probably should have tried something else to not give you false hope that this is always a really straightforward process. Okay, sometimes you got to try a bunch, but not any more than 6. This isn't too terrible, right? You could do this 6 times and survive to tell the tale. Okay, so now we know that f of x equals x minus 1 times 4x squared plus 4x plus 1, right? Those coefficients from our synthetic division. Okay, now we've got a quadratic. Can we factor this? Maybe. But if we couldn't, let's just use the quadratic formula. X is going to equal minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so what happens here? We get minus 4 plus or minus 16 minus 16, 0, all over 8. So that's just minus 1/2. What does that mean? We wanted to get 2 roots and we only got 1. We've got 1 factor here. It means that there's a multiplicity going on. Okay, maybe this root is repeated. We can try it out, right? If our factor is negative 1/2, then let's use polynomial division on this. Let's divide it into here and see what we get. 1/2 times 4 is 2. Oh, wait. You know what? This is minus 1/2, so this is supposed to be minus 1/2. So bring that down, I'm going to get minus 2, and then here I get 2, negative 1, 0. So what's going on here? We know that one of our roots is negative 1. We know our other one is negative 1/2. And now we're left with 4x plus 2. Are these the same? Yes. If we put negative 1/2 in here, or negative 1/2 in here, they are both 0, right? So what was this question asking? It said find the zeros. Okay. So our zeros are going to be, zeros are x equals 1, negative 1/2, and negative 1/2, right? We could set this term equal to 0 and solve. It would give us negative 1/2. So we could write it like this. We could just include one of the negative 1/2s, right? And say that that has multiplicity 2. Okay, so let's think about what we did here. We had a polynomial. We wanted to find the zeros. We listed the possible rational zeros using the rational root theorem. We tried one and it worked. First one off. So we could write it like this linear factor times the quadratic using those coefficients. There we go. Now we had a quadratic. We used a quadratic formula. We could have factored this, right? It is factorable. But we just used the quadratic formula. We found another root. And we said, okay, well, what's left? We used the synthetic division to find the third linear term, or linear factor. And from those linear factors, we use the fundamental theorem of algebra, or just kind of what we've been doing forever, to use those linear factors to list what the roots of that function are. Okay? And if we look at the graph of this function, we said our roots were 1. Sure enough, it crosses. It had multiplicity 1. And let's bring this back around to what we did last week. Here is the other root at negative 1/2 that had multiplicity 2. And do you remember, if a root has even multiplicity, what does it do to the graph? It touches and turns, right? Aha, touches and turns, just like we expected. All right, let's do it again. Let's do another example. Let's do example 6, which is here. Find the zeros of this polynomial. Okay, phrasing just like we had last time. So we're going to go through the same stuff, right? We're going to find any rational. We have a cubic. We've got to, if we find one linear root, then we have a quadratic and we can solve it. So we are going to try to find a root using the rational root function or whatever, or theorem. All right, so factors of 3. We're going to be plus or minus 1, plus or minus 3. Factors of 3. Plus or minus 1, plus or minus 3. Okay, so possible rational roots. So this over this, this over this. So plus or minus 1, plus or minus 1/3, plus or minus 3 over 1, plus or minus 3 over 3. So what does that mean? Let's simplify these. It could be plus or minus 1, plus or minus 1/3, plus or minus 3, and then this is going to be the same as plus or minus 1. Oops, sorry. There you go. So we have 6 possible roots. Let's see if my magic works again. Let's just choose one because it's easiest. All right, we're going to plug these in. Using synthetic division, our coefficients are 3, 9, 1, and 3. Let's try 1. 3, 12, multiply, add, Nah, didn't work. Okay, so this isn't a root. It's bound to happen. Let's try -1. Okay. Add, multiply, add. Nope. Struck out again. I'm going to try 3 next just because, I don't know, fractions look kind of... Let's try 3. You know what? I'm just looking at this. There's not any negative numbers here. So there's no way that 3 is going to work. I'm going to try -3 instead. Right? Let's see if that works. I bring that down. -9, 0, -3, -2, 6, 9. That didn't work. I'm going to try -1/3. Okay, this is a good, better, true-to-life example where sometimes you got to try a bunch. Okay, so I bring this down. I get -1, 8, -8/3. 1 minus 8/3 is -2/3. No. -5/3. Okay, and this is going to be something. -5/9, whatever. 3 minus 5/9 is not 0. Okay, so that didn't work. Huh. All right, either I'm doing something wrong or we're about to find one that works. Maybe it's +3 would work. Let's see. No, see, this is just going to get really big. I don't know, what is that? 56, 57, something big, 171 or something, 174. All right, so maybe +1/3. Uh-oh, did I make a mistake somewhere and you guys have all been watching this video, like yelling at the screen, like, stop, you made a mistake. It's very possible. There's no way this is working. I don't know, something. Okay, so I made a mistake somewhere. Let's go back and check my work. It's kind of stressful to make a mistake on a video. Okay, let's try one. Let's try this -1. This one looks like it. Maybe I made a mistake. -3, 6, -6, 5, -5, 2. Nope. All right, let's try this one. 3, -9, 0. Oh, I did make a mistake. 3 times 0 is not -3. 3 times 0 is 0. Okay, so now we add this, and we get 1. -3 times 1 is -3, and this is 0. Okay, well, we got lots of practice in synthetic division. But now we know that -3 is a 0. All right, so it happens to the best of us, guys. You just got to go back and find your work. Look, this is a good example. The more clearly you write out all your work, the more you can just go back and find where your mistake is. See? It's a good teachable moment. All right, so now we know f of x equals, here's our good one, x plus 3 times, what are we left with? 3x squared plus 1. Right, that's a plus 1. 3x squared plus 1. It's a quadratic. We can solve a quadratic, right? All right, let's do it. X is going to be minus b. What is b? 0. Plus or minus the square root of b squared, 0 squared, minus 4 times a times c, all over 2a. All right, so it's going to be plus or minus the square root of negative 12 all over 6. Move this up. All right, let's simplify this. First thing we're going to do is bring that I out and write that as 12. And 12, let's see, I can write that as 4 times 3. So I can bring a 2 out, right? Plus or minus 2i square root of 3 all over 6. And I can simplify this and get plus or minus square root of 3 over 3 times I. Okay, so those are two complex zeros. This is the first time that we've gotten complex numbers as zeros of our polynomial. Okay, so we can list the zeros now, right? The zeros are negative 3 and plus or minus square root of 3 over 3 times I. That would be my solution. And that's what we'd expect. Just sneeze. Okay, we have a third degree polynomial, and we got 3 zeros, including 2 complex zeros, right? So including complex roots, we get 3 zeros. And if we go back, I think we get a graph here, right? At negative 3, that was our real zero. It crosses the graph. It had multiplicity 1. And that's the only place it crosses the graph, right? Our other zeros were complex, so they don't correspond in any way to like where it crosses the x-axis. They don't really correspond in any straightforward, easy way to what's happening with the graph. Okay, so it's not like this function, this point here, like has to do with them or something. Nope, they just don't really correspond to the graph in a straightforward way. All right, we did it. We found those zeros. If these feel like kind of a lot of work, they are, right? These just take a little bit of time. They're a little bit of work, and we just keep going. Even if we make a mistake, we just go back and find our mistake and then carry on. All right, here is the complex conjugate theorem, and the problem we just did kind of hinted at this. It says, according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree. And each factor will be in this form, where c is a complex number. Okay, so just what we were saying. We had a third degree polynomial. We found 3 roots, including 2 complex roots. So if the polynomial function f has real coefficients and a complex 0 in this form, then the complex conjugate is also a 0. Okay, if a plus bi is a 0, a minus bi is also a 0. They always come in conjugate pairs. Okay, so if you find 1, you get 2 for the price of 1. All right, so let's do this one. Find a 4th degree polynomial. So what does that tell us? It's going to have 4 zeros with real coefficients that has these zeros such that f of negative 2 equals 100. Okay, so they give us 3 zeros. We know there's 4. What's the 4th one going to be? Well, we know if we have one complex 0, an I, so we know its complex conjugate is also going to be a 0, which would be negative I. Okay? So we can write this out. F of x is some constant times x plus 3, x minus 2, x minus I, x plus I. Okay, we write each of these linear factors, and they multiply them out. Okay, they multiply the x plus 3 and x minus 2 and get this. They multiply x minus 1 and x plus 1 and get this. That's what we expect because these are complex conjugates, right? So the imaginary part actually disappears. And then they multiplied all of this out. You don't really, for me, you don't have to multiply all these out. I don't think for your homework you're going to either. I think you could write it just in this form. Okay, you don't have to multiply all these things out just to get a nice looking polynomial. Okay, however, that's what happens. If you multiply all these linear factors, 4 linear factors, you get a 4th degree polynomial with some constant out front. How are we going to figure out what that constant is? All right, this is a theme that keeps coming up with different kinds of problems, right? If you've got a constant, how can you solve for it? Well, we've got a point on that polynomial, right? We know if x is negative 2, f of x is 100. So, ta-da, we put in 100 for y, and we put in negative 2 for x, and multiply it all out. Okay, negative 2 to the 4th, negative 2 cubed, da-da-da-da-da. And they don't show us their work, but they, put all the stuff in their calculator or figure out what it is, and they get added all together, it's negative 20. So 100 equals a times negative 20, divide, and you get that a equals negative 5. So they put it all together, and they put negative 5 in for a. They could multiply it through all the terms. You don't really have to, okay? But that's how we do it, okay? If they tell us the zeros, we can write the linear factors, and we times a constant. We can't forget the constant, okay? And then we could use this point to figure out what that constant is. All right, we've got one last little tool, and this is kind of a novelty, all right? Descartes' rule of signs. So, back in the day, they didn't have graphing calculators or computers to just quickly graph a function and see where the zeros were. So they had to have all kinds of tricks to figure out what the zeros were, right? Doing what we're doing is a little bit of a vestige of that, like the olden days where like mathematicians found zeros of functions instead of just graphing them on Desmos, right? You could not understand anything about math and still be able to figure out what the zeros were just by typing it into Desmos, and voila, there's your graph. You can see the zeros. But back in the day, they could not do that. And so mathematicians sat around and tried to think of clever tricks to help them figure out what was going on with these functions. And Descartes was one of these mathematicians. So here's a trick that he came up with. Descartes' rule of signs. All right, so we've got a polynomial, and it has real coefficients. All right, this is also surprising and kind of interesting. The number of positive real zeros is either equal to the number of sign changes of f of x or is less than the number of sign changes by an even integer. The number of negative real zeros is either equal to the number of sign changes of f of minus x or is less than that by an even integer. What is this even talking about? All right, here's a polynomial. This is what it means. Let's look at f of x. Here we go. It's just the same polynomial. We look at, this is negative. This term is negative, negative, positive, negative, negative. Okay? What this is saying is, look at the sign changes between terms. Negative to negative is not a sign change. Negative to positive is a sign change. So there's this little arrow. Positive to negative is a sign change. So here we've got this little arrow. Negative to negative, not a sign change. So you're literally just looking at the terms and seeing if the sign is changing from term to term. This has 2 sign changes. Okay? So what Descartes' rule of signs is telling us is there will either be 2 or 0 positive real zeros of this function. Okay? So the way they phrased it was that number of sign changes or less than that by an even number. So if there were 7 sign changes, there would be 7, 5, 3, or 1 positive real zeros. Does that make sense? We're never going to give you a problem like that. All right, there's 2 sign changes. So there's either 2 or 0 positive real zeros. Those are how many there could be. All right, now let's look at f of negative x. This takes a little more work because you got to plug a negative x in, right? Negative x to an even function is just x to the even power is just x to the fourth. Negative x to an odd power actually changes, is going to be negative x cubed, and that changes that sign, right? This doesn't change the sign. This does change the sign. That doesn't. Okay, just take a minute. You can pause the video and just see how they got from here to here. And once you've done that work, now we literally, again, just look and say negative term to a positive term. That's a sign change. Positive to positive, not a sign change. Positive to positive, not a sign change. Positive to negative, yep, that's a sign change. So this has two sign changes. So the possibilities are either 2 or 0, negative real zeros. Okay, if there were 2 positive and 2 negative, there would be 0 complex. If there were 2 positive and 0 negative, then there'd be 2 complex, right? Because this always has to add up to 4. Our possibilities are positive real zeros, negative real zeros, or complex real zeros. Or sorry, not real, just complex zeros, right? Between these 3 numbers, they have to add up to 4. So this column we're just filling in to make this equal 4. Okay? If we had 2 and 0, we'd need 2. If we had 0 and 2, we'd need 2. If we had 0 and 0, maybe all of the roots are complex. That can happen, but they always are going to add up to 4. Okay? And if we look at that function from the last slide, here's what it looks like. It turns out that it has 2 negative real zeros. Okay, so it was this case here. We had no positive, 2 negative, and 2 complex zeros for that function. So that's like, again, that's truly just kind of like an old-timey novelty, the Descartes rule of signs. I wouldn't worry too much about it. Of all the tricks we talked about in this section, the most important and most useful is the rational roots theorem, right? We use that in every example that we did where we actually had to find the zeros. All right, so that was kind of a lot, but the main idea, again, is the rational roots theorem, knowing that you can, it gives you a place to start to try to find factors until you can get your function down to a quadratic, in which case then you use the quadratic formula or factor to find the rest of the zeros, okay?